2.5?
2.37. Or 0.237.
0.237.
Meters.
Are you sure? Seems like that should be 1 point.
Oh yeah, I put it in.
Okay.
Hey, where did you get .03 from?
Looking at the difference here, the 0.05 minus 0.02,
Okay.
and then, so change in mass over change in position.
I got you.
In essence, finding the slope of that line.
So,
Good
we
work.
took .355 and subtracted that from 2.231?
Yes.
Okay.
Yeah.
Why would you do like change in mass when it's just M?
Because I was sort of picturing finding the slope of the line, and so, I mean, there's no reason why you can't do that. But if you wanted to just look at the mass, I mean, you could pick those. I went with those because Ethan said so. He spoke first, or I heard him first.
Can you do a linear regression too?
Yes.
Okay.
What are the units here?
Meters, or newtons per meter.
There we go. All right, so that's number 8A. B, we attach a 20-gram mass to it. It's stretched to 48 centimeters and released. The period of the harmonic is 0.919 seconds. What's the effective mass of the slinky? Oh, sorry, with the 20-gram mass attached, it's stretched to 48 centimeters and released. So I'm interpreting that as with an equilibrium, that is where it is, but then it gets stretched down to 0.48 meters. So the amplitude is the difference between those two. 0.249 meters. The period is 0.919 seconds. Let's get some room here. Whoa, that's more than I wanted. There's my period. That's going to be equal to 2 pi times the square root of m over k. My mass is the mass of the 20 grams plus whatever the effective mass of the slinky is. So I get 0.919 is equal to 2 pi times the square root of 0.02 plus the effective mass of the slinky divided by 2.37. It's now a calculator exercise, or calculator and algebra exercise. Once we have the effective mass, the part C is if we now use the 50-gram mass instead of the 20-gram mass, what is the period? And so whatever we get from that, for part C, the period is going to be 2 pi times the square root of 0.05 plus the effective mass divided by 2.37. Did anybody calculate the effective mass?
0.931 kilograms.
So this becomes 2 pi times the square root of 0.081 over 2.37. And that would be the answer to C. Questions? It's the ghosts.
.05.
So part B is you're trying to find the effective mass of the slinky. Part C, you don't use, you take the 20-gram mass off and you put on the 50-gram mass.
Oh, you replaced it, okay.
Yeah. And then for number 9, just like the song, if you can call it that. A string from a guitar is held fixed at both ends. If it's fixed at both ends when it's in a harmonic, are those nodes or antinodes?
Nodes.
Yes. Nice synchronized answer there. It's the third harmonic, so I know that's the first harmonic, second harmonic, third harmonic. So this is the one we care about. Vibrating length of 30 centimeters, so this distance right here is 0.3 meters. And so the first question is, what's the wavelength of the transverse wave as opposed to the sound wave? And also side information for later in the problem. 400, frequency is 400 hertz. What's the wavelength of the transverse wave? In other words, the wave on the string.
Is it 3 halves times 0.3?
No, like, where do you get 3 halves from?
A half, 1.5.
Yeah. So it's 3 halves of a wavelength is equal to 0.3.
Oh, so it'd be 2/3.
Yeah. Which is 0.2 meters. A wave will go from, basically that's the wave, it's 2/3 of the whole thing. The speed of the wave on the string. Well, I have wavelength, I have frequency. Speed is frequency times wavelength. So that's 400 hertz times 0.2 meters. Doing the fancy math there, 80 meters per second. Bless you. Then the next part is exploiting the fact that we have 2 formulas to find the speed of the wave. The speed is frequency times the wavelength, and it's also equal to the square root of the tension over the linear density. Well, we already found the speed, so it's equal to 80. So 80 is equal to the square root of the tension, which is what we're trying to find over that. And I give you the information for it. Information I give is 0.4 grams, 1.4 meters, so 0.0004 kilograms over 1.4 meters. And solve for tension. And then the last one is, what is the wavelength of the sound of the sound in the air? I give it room temperature, so the speed of the wave is about 340 or so meters per second. And remember, if I gave it speed of sound in the air, about 343 meters per second, so that's on the front page. V is equal to the frequency times the wavelength. This is 343 meters per second. Is equal to 400 hertz times the wavelength. So the wavelength of the sound in the air is 0.85 meters-ish. $85.75.
Yeah.
minutes to spare. Just think how fast it's gonna go if someone were in front of you talking the entire time. Go ahead.
The test tomorrow only gonna be on rotational and, this stuff.
And energy and momentum. Chapters 7, 8, 9, 10, 16, 17.
Easy on top.
All right, what was that, Chris?
Take it easy.
Lead.
You know, I bet you never done this